can arrive at the same solution for the least squares problem by using linear algebra. Let X be this matrix and Y be the column vector y1 through yn as before from our training data. We want a vector beta. Okay, so let me write that here. We want a vector beta such that x beta is close to y. In other words, we want a vector beta such that the distance the distance between x beta and y is minimized. Okay. A vector beta that minimizes this distance is called a least squares solution of x beta equals to y. Okay, now note that x is an n by p plus 1 matrix. We want a beta hat in R p plus 1. Okay, we want beta hat in R p plus 1 such that x beta hat is closest to y. Okay, note that x beta hat is a linear combination of the columns of x. Okay, so x beta hat lies in the span of the columns of x, which is a subspace of Rn denoted like this. Column space of x. Okay. So we want the vector in the column space of x that is closest to y. The projection of y onto the subspace column space of x is that vector. Okay, so the projection of y onto the column space of x is going to be equal to x beta hat for some beta hat in R p plus 1. Okay. Now, the reason for that is that the projection of y onto the column space of x is going to be a linear combination of the columns of x. Okay, so here beta hat represents the weights for that linear combination. Okay, so take a look at this graph here. This space down here, that's the column space of x. Here we have y, the vector y, and we're projecting that down onto the column space of x. Okay, and that's going to give us something here, x beta hat, okay, for some beta hat. Okay, now consider y minus x beta hat. Note that y is equal to x beta hat plus y minus x beta hat. Okay, here notice x beta hat just cancels out and we get y, so that's why this is true. Okay. Now this right here, this lies in the column space of x. Okay, now look at this. This thing here, that should be in the orthogonal complement of the column space of x. Okay, now why is that? Okay. Well, so Rn can be written, Rn can be broken into two subspaces, column space of x and the orthogonal complement of column space of x, written like this, where this is the subspace of Rn consisting of all vectors that are orthogonal to the vectors in the column space of x. Okay, now any vector in Rn can be written uniquely as z plus w, where z lies in the column space of x and w lies in the orthogonal complement of that. Now, since y lies in Rn and y equals to this with x beta hat in the column space of x, the second vector, y minus x beta hat, that must lie in the orthogonal complement of the column space of x. So let me write that here. Okay. Okay, so now the reason why is because y is equal to something which lies in the column space of x plus something else. But that something else has to lie in the perpendicular, the orthogonal complement of the column space of x, because any vector in Rn, okay, any vector in Rn can be written uniquely as the sum z plus w, okay, where z lies in the column space of x and w lies in the orthogonal complement. So that's what we said here. Okay. So therefore, y minus x beta hat is orthogonal to the columns of x. So if we take x transpose times y minus x beta hat, we get the 0 vector. Multiply this through, we get this. Okay, now bring this over to the other side, we get this. Okay. Thus, it turns out that the set of least squares solutions of x beta equals to y consists of all and only the solutions to the matrix equation x transpose x beta equals x transpose y. Now, if x transpose x is positive definite, then the eigenvalues of x transpose x are all positive. Okay, so 0 is not an eigenvalue of x transpose x. Okay, it follows that x transpose x is invertible. Then we can solve the equation x transpose x beta hat equals to x transpose y. We can solve that to get beta hat equals to this, which is the same result we got earlier using multivariable calculus.